Well, hi, everybody, and welcome to a demonstration about a pendulum. So the idea here is to perhaps review something that you covered in your dynamics class, but also to illustrate how we can use the first law to better understand and compute what's going on with this pendulum. And so here we go. I have an assistant somewhere in the workshop. Tigger is talking to me, so he may appear while we're working on this. So the objectives of this little demonstration are to determine and verify that we can both calculate and also measure the period of oscillation of this pendulum. Then we're going to use the first law for a closed system to determine the maximum values for potential energy and kinetic energy for this process. And we're going to be able to determine the maximum velocity. So let's look real quickly at this pendulum. Obviously, whoops. Let me quit sharing again. Okay, here we go. So the pendulum, I think you've got it in your view. I've marked, here's what I've done here. I've marked the center line, right here, right there. Oh, and there goes little Mr. Tigger, my assistant. Kinetic energy and potential energy. Let's look at this where the pendulum reaches its maximum swing. Let's see. What's the kinetic energy right when it stops? It makes its turn and stops. Well, the kinetic energy here is going to be 0. And do you see that also at this maximum point here, the potential energy will be the biggest value because the height of the weight above the ground is the most, okay? So how about this middle point here, this middle point? Well, we're going to say that the potential energy here, we'll set the datum as the center line, the center of gravity of the mass. So the potential energy here is going to be 0, but this is where we're going to have the maximum velocity. So the kinetic energy at this minimum point is going to be the maximum kinetic energy. Okay, so you're getting the idea. All right, let's go back to the slides. Okay. So here's our sketch. Let's start with a sketch. So we're going to turn this into like a homework problem, and we're going to have a sketch. And so what I've shown here on my screen is the minimum. Let's say start 1. Let's start here at state 1 at the maximum position where the height is the highest. Okay, and I hope you saw here in the real world, the potential energy is the maximum value, and the kinetic energy, right where it makes its turn, right where it turns from going one direction to the other, the velocity has to be equal to 0 there. So the kinetic energy at the high point is 0. How about the low point? Well, at the low point, we're gonna say our datum line Z equals 0 goes right through the center line of the mass. Okay, so the potential energy is 0, and the kinetic energy will be the maximum because that's where the maximum velocity is. I've done some pre-work and measured the length of this is a chain, so it's a chain supporting 20 pounds plus of iron weights. 92 inches of chain, the length of the pendulum, 92 inches. The mass is 9.85 kilograms. So there's our sketch. And so the system, what's the system? The system is going to be the mass, the pendulum mass. So that is our closed system. Let's go remind ourselves. Now, I could not remember by heart. It's been a long time since I took dynamics. And so I had to go back to Wikipedia to remind myself, what is the period of oscillation of a pendulum? And we do the reading, and we discover that the period of oscillation T is 2 pi times the square root of L, the length of the chain, divided by g, acceleration due to gravity. Okay. And then there's another stipulation for this to be valid, and that is the starting angle, the starting angle theta naught must be less than 1 radian. So we're going to do the math to determine when we do this experiment on what is the period, we'll determine how far I need to pull the pendulum back from its resting point. Another interesting reminder for me, and I'm going to have to say, when I started out doing this, I had forgotten that the period of oscillation does not depend on the mass of the pendulum. So that's kind of amazing to me that the period doesn't depend on the mass. It really doesn't matter what the mass of the pendulum is. It depends only on the length of the pendulum. And of course, acceleration due to gravity for us is a constant. All right, so let's look at the, so looking ahead, we've assigned, we're going to be able to compute the maximum potential energy. We'll look at the first law to show that the maximum potential energy exactly equals the maximum kinetic energy, okay? And so maximum potential energy. Well, let's say what we're going to do is we're going to, on our kinetic energy deal, we're going to pull this X, we're going to pull it way, way back so we can really get some good movement on our pendulum. And so do you see, if we pull this pendulum back a distance X, what we need to do to get the potential energy is determine H. So we have a trigonometry problem, right? So here's theta, and therefore here's theta. And so let's see, how do we determine theta for a certain amount of pullback? Well, theta is the arc sine of X over L, okay? And then, so then we can determine H, how high is our pendulum? Well, it's X times sine theta. So it's really pretty easy. And so the maximum potential energy is simply going to be at state 1, m, the mass, times g times h. So that's the maximum potential energy. The next thing we're going to do, coming right out of thermo class, is let's write down the first law of thermodynamics. Okay, the closed system is the pendulum ball. Okay, you're looking at it with your eyes. There's no heat transfer associated with this process. The ball itself, or the mass is not lifting away. Now the system is moving, isn't it? The system is dynamic, okay? But the ball, the ball or the mass is not lifting a weight. So there's no work being done from a thermodynamic standpoint. And also this weight that you're looking at with your eyes, it's not changing its internal energy, is it? The temperature of the mass is not going up, not going down. Let's write the first law then and see what we get. Q in minus W out equals delta U plus delta KE plus delta potential energy. And look, I've struck all those things out by observation, okay? So delta KE plus delta PE equals 0. Let's put in our little nomenclature from our sketch. Kinetic energy change, potential energy change. Now, at state 2, which is the lower position, the resting position, the potential energy is 0 because we drew our datum right through the center of the mass. At state 1, that's going to be the pullback position. The kinetic energy is 0 because, well, we're going to start it out there where there will be no velocity, but also recognize that's the point where it turns from going in one direction to the other direction, from positive to negative velocity vector. So therefore the velocity at that point is 0. So wow, now we're 0 equals kinetic energy at 2 minus potential energy at 1. We'll do our substitution of what we know in thermo. Kinetic energy at 2 is the mass times V2 squared over 2 equals the potential energy at 1, mgh. Right, kinetic energy max equals potential energy max equals mgh. And so finally, what we want to find, what's the maximum velocity for our little experiment, when it reaches its lowest point, that's where the velocity of the mass is the maximum, and it's simply the square root of 2gh. All right, so we're almost ready to go live. Our first step is going to be to verify the period of oscillation. Okay. Remember that theta has got to be a small number, and so I've picked 0.2 radians I picked 0.2 radians as where I want to start the swing when we do our experiment of measuring the oscillation period. Okay, that turns out to be 11 degrees. 0.2 radians is 11 degrees. Okay, and then for those 11 degrees, we can solve that the maximum swing to start out with for our period test is going to be 18.4 inches. And I've got that marked for my, that sort of, those are just nut drivers down on the ground. So that little second mark is going to be 18 inches. Okay. And then, and so the theory says, so given this situation with our length of chain, the theoretical period is 3.1 seconds for a period. So we will now, let's see, I'm going to stop sharing and we'll go live. All right, so here we are at the resting position. Okay, resting position. I'm going to pull it back. I'm going to pull the mass back to 14 inches and then let it go. And as soon as I let it go, I'm going to start my stopwatch and we're going to go 10 cycles, and I'll try to count them off to keep myself straight. All right, so I got my stopwatch is ready. I'm going to pull it back to 14 inches and I'll count each period. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I've got my number here, and it's 30 in 10 periods, 30.38 seconds. And we're going to do the math here in a second. All right, so that was our first trial. The next thing I want to do is I really want to pull way back on this weight to really get some motion here. And it's going to be, I'm going to pull the weight back 36 inches. Okay, so that's around a meter, right? 36 inches. And then we're just going to see and watch and see what we have for a pretty decent swing on this thing. Okay, I pulled it back. I'm trying to eyeball what I've got. I pulled it back 36 inches. And I'm going to let it go. Okay, so we've got some pretty darn good swing. So this is my demo. And so what I do want you to see, just sort of looking, notice how we've got the, it's a little hard to see, but clearly you can see the velocity vector change from plus to minus, okay? Therefore, the velocity is 0 at right there, okay? So 0, and then we get to the minimum position, the lowest position of the pendulum, and that's where the velocity is going to be a maximum. So, oscillatory motion. So now you see with your eyes a closed system. It's a pretty simple closed system, a simple thermo problem, and the simple closed system is made up of the weights that I've got suspended from this chain. Okay, let's go do the math. So I'm going to go to Excel. And if I can restore my 30.38 seconds. So we went 10 cycles. Can you see what we've got? 10 cycles, 30.38. Okay, so our observed period is 3 seconds. I think it is so cool. I think it's so neat that our experiment is validating the theory. That's pretty darn good agreement. Okay. The next thing we did was, okay, so then I'm going to scroll down. The next thing we did was I pulled the pendulum back 36 inches. I pulled it back 36 inches from the minimum point. Okay. Did the math. So the starting angle is 23 degrees. I solved for the starting angle, 23 degrees. The starting height in meters is 0.358, the height above the datum, 0.358 meters. Okay. So the next thing we're going to do is, okay, so there's H, put that in, G from above, 9.8. The mass, 9.85 kilograms. So the maximum potential energy exactly equaled the maximum kinetic energy of 34.54 joules. We go through the math. Okay. So we've got the ability as engineers now to sort of calculate some things associated with a pendulum. Okay. And the maximum velocity then, Vmax, again, we're just going to go in and do what we derived. 2.65 meters per second is the maximum velocity. Okay, let's see. I'm down here. I've got to go back to PowerPoint to finish up. Okay, we just saw that in Excel. We did the math. And now for example, so you might say, well, what? Okay, who cares about a pendulum? So, so what? So what? Some applications, tried and true timekeeping. I hope you've seen a grandfather's clock around somewhere. But this guy, Christian Huygens invented the clock in 1656. And so that has, up until recent times, with electronic methods, which are much more accurate, this guy revolutionized the way that people kept time with pendulum clocks. Okay. We don't use those much anymore. We really depend on electronic methods to keep time now. Another application, the wrecking ball. You can still see these in operation when it's demolition time. And so here's a great example of a big mass wrecking ball that has just wrecked into, has just swung into a brick building, causing a gaping hole. Here's a great image of a crane operator swinging a wrecking ball. It's almost like a classic pendulum. And the point to make there is the chances are that this crane operator probably does not have an engineering degree. Okay. But that crane operator has got a physical feel for the physics of what's involved. That crane operator has a physical feel for exploiting the relationship between potential energy, how far the pendulum swings back, kinetic energy, how fast it starts moving, and the transfer of energy from that pendulum ball into what you're trying to wreck. And so this is a very classic application of a pendulum. And then finally, the metronome. For those of you that are musically inclined, have some musical experience, musicians use the metronome, which is an inverted pendulum, to practice their craft and maintain a certain tempo when they're practicing. And so there you go. Let's see what we accomplished. We refreshed our memory in Wikipedia to predict the period of oscillation of our pendulum. You can still see, I think you can still see the pendulum going. Okay. We use the first law of thermodynamics for a closed system to determine the maximum kinetic energy, the maximum potential energy, both of those are the same, and the maximum velocity for a pendulum. So that's it. I thought you might be interested in seeing another little demo. So once I get out of here, I will stop recording, and we'll see you next time.